Hey everyone, it's your math teacher, Mr. Boyden, back at it again today, and I'm really excited today because I'm going to be unveiling a couple new kinds of technology. I've got a new headset that I'm using with a new microphone, so hopefully that sounds good, and hopefully it isn't killing your ears to listen to me, any more than normal at least. I've got a brand new writing pad, so I can now actually write on the screen without touching the screen. So I can write my name, and hopefully my penmanship is at least as good as in class. And so I'm going to be a little bit clumsy today, but that's what I'm going to be writing with, and I'm going to try to do a good job so it's really clear. And then also I have a TI emulator that's going to make its first debut today, so you can see what I'm typing in the calculator, even though I actually don't have a calculator with me right now. I'm making this video at home today, and all the calculators are at school. But I have one on the computer anyhow that I'm going to debut, so you can see that. So let's get into our lesson. This is going to be the final lesson in our integral series for right now. We're going to talk a little bit about particle motion and kinematics. This is an application that often comes up, and it's one of the ways we can use integrals to actually do stuff. So let's look at a really simple example just to start. And here we have two cars, and we want to know how far each one of them traveled. Okay, so let's take a look at this first one on the left. First thing to notice, car is going 60 kilometers per hour. I know it's hours to the -1. Just think of that as being in the denominator, kilometers per hour. So it goes 60 kilometers per hour, and how long does it do that? Looks like it's doing it for 1/4 of an hour. So we can figure out that 1/4 of an hour multiplied by 60 kilometers per hour, and I'm going to write it as a fraction, we can figure out pretty quickly that if that's what we have, then we can cancel out the hours with the hours. And so we have 1/4 of 60, which would be 15 kilometers. And that's how far it traveled. Okay, so that's not super hard. Let's look at how calculus plays into it. And yeah, we're starting with a really simple example, but it's important that we understand what the calculus is that goes along with this so that it can make really good sense. All right, I'm just playing with my line thickness here. All right, so here's how I do that. Notice up here that this is an area and it's shaded in, so that suggests to us that perhaps this is an integral. So let's set that up. Okay, so integral, and we're going to put in our function. Our function, what would you call that? It's constant, it's horizontal, it's linear, and it's happening at a y value of 60. So integral of 60. This axis down here is t, so we're going to call this not dx, but dt. And that'll make sense because when we plug in our bounds, it looks like we're going from 0 to 1/4. So, 0 to 1/4. And so now we can integrate. Okay, so remember, we're doing the add and divide rule. And so this has no variable with it. Well, now when we integrate, we're going to get a variable. And so we're going to get 60t. We've done that. And now we've got our bounds from 0 up to 1/4. And so we plug that in. And now we get a 1/4 plugged in. And that matches exactly the work we had up here. So that we already know that that's 15. And then we're going to subtract, plugging in a 0. Well, 60 times 0 is 0. So we get our same result. Now, that was pretty easy. And actually, we showed up above that we didn't need to use calculus to figure this out. But imagine that you're in stop-and-go traffic, and so you end up with a graph that looks something more like this. It's up, and it's down, and it's 0, and then it's up, and then slam on the brakes. And so it would be a lot harder to figure that out without calculus. But if you just take an integral, shade that in, then you'll know exactly how far the car traveled. Okay, we've got our other example over here on the right, the one in the purple. So let's take a look at that. Okay, with this one, very similar. This one, we have a little bit more interesting a function. However, on this one, I'm actually going to basically use a Riemann approximation. Think back to like the trapezoidal rule. This one happens to be a triangle, and so if I want to know how far this car traveled, what I need to know is this shaded area. And that's pretty easy. Remember, that's a triangle, so that's 1/2 base times height. We're just going to fill those in. So that'd be 1/2. The base looks like it goes 0 to 1/10, so that would be 1/10. And then our height is 60. Let's do a little bit of mental math. 2 times 10 is 20. So we have a 20 in the denominator and 60 in the numerator. 60 divided by 20 is 3. And what are our units? That's also kilometers. Okay, so that's a really basic intro to how this concept could be useful to find distance traveled or things like that. And that's particularly useful in a case like this one, where we don't have a consistent deceleration or a consistent speed, but where we have wild fluctuations happening over time. I'd like to offer you a friendly reminder now. We need to remember position, velocity, and acceleration. And so we've used this a little bit. We use it a bit, especially with derivatives. We also need to remember how it relates to integrals. And we saw that just a minute ago. So a minute ago, we had an integral of velocity with respect to time. And what did that represent? That represented our distance. Now, distance is nothing more than change in position. And so that relates back up here. Okay, so we move from velocity, an integral moves us upward. And so we get our change in position. So what if we took an integral of our acceleration? What would that mean? Looking over here, make a prediction. Okay, so integrals work up the chart, derivatives work down the chart. So if you take a derivative, or excuse me, an integral of the acceleration with respect to time, then what do you get? You get how much your velocity changed. I'm going to call it delta v. Or you could say, if you started at 0, you'd have your actual velocity. We're going to get into that a little more in just a minute. Okay, let's look at a visual example. Here's one with a graph. The graph is going to represent the velocity of a train, and it's going to do a 36-minute trip. Notice the way this is labeled. They say 0.6 hours, and you'll notice that 0.6 hours is the same as 36 minutes. Okay, so that lines up. We want to know how far did the train travel in that time. Okay, so that goes directly back to what we just talked about. Distance traveled is going to be an integral of velocity. So we need to integrate this. Now, it's not necessarily asking us to write out a whole bunch of integrals. I mean, we certainly could. I mean, we could say, hey, this is the integral from 0 to 0.6 of the velocity function. And the axis here is time, so with respect to time, or dt. And the problem is we don't have an equation for that. And yeah, we could write this as a piecewise with 1, 2, 3, 4, 5 pieces. I'm going to suggest we don't do that. That could be quite a lot of work. So what we'll do is we'll do this by finding the area. We can break this down into shapes that we know. Okay, so let's break it down into a triangle. Oops, kind of ugly the way I'm drawing that. So a triangle, looks like we have a rectangle right here, a trapezoid, a rectangle, and then finally a triangle down here. Okay, and so I'm going to call these regions 1, 2, 3, 4, and 5. And I'm going to label those just so when I reference them verbally, you know which ones I'm talking about. And so what we're going to do is we're just going to go right down the line and we're going to find the area of each of those. Okay, and so I think I'm going to index these here. So I'm going to say 1, and then right here I'll have my work for that first area. Okay, so that's a triangle, and that tells me that it's going to be divided by 2. Remember, it's 1/2 base times height, or base times height divided by 2. The base of it looks like it's probably 0.1. 0.1. The height goes from 0 up to here. I have to be a little bit careful. I'm going to count 10, 20, 30, 40, 50. Okay, it is counting by tens, so that's 50. So times 50. And now I'm going to go on and I'm going to continue my setup. Okay, so this next piece of work is going to correspond with interval number 2. Interval number 2 is pretty easy. It's a rectangle. It goes from 0.1 to 0.3. So that is a width of 2, or excuse me, rather 0.2. And it has a height, same height as before, so times 50. And it's not divided by 2. It looks like I almost started to write it. It's not divided by 2. It's a rectangle, so be careful. Okay, going on to our third one. That appears to be a trapezoid. So we need to remember our trapezoid formula. That is base 1 plus base 2. So something plus something times the height divided by 2. Okay, the bases, remember, those are the sides that are parallel. So we got to find the heights of those. First one is 50. So 50. Second one is 30. 30. And then the height is going to always end up being that delta x. That was back from the very first video. Okay, so this is very similar. We're sort of, except this one's not an approximation because this isn't a weird curve. These are all linear. We're going to have it exact. But in our first video, we did trapezoid approximations and they weren't exact because those were curves. But this height, nonetheless, that's 0.1. We need to go to region 4, and these are going to start to get a little bit easier now. Rectangle with a width of 0.1 and a height going up to 30. And then finally, we're down to that fifth region. We've got a triangle with a width of 0.1 with a height of 30. and we're going to divide that by 2 because we know it's a triangle. All right, let's simplify this thing, and we're going to be able to figure out how far this train traveled. All right, we're going to just go piece by piece here. 0.1 times 5, that is 5. Or excuse me, 0.1 times 50 is 5. So I've got 5 halves right here. Plus 0.2 times 50, I believe that's 10. Plus, we've got 80 times 0.1 is 8. 8 divided by 2 is 4. 0.1 times 30 is 3. And 0.1 times 30 is 3, so that is plus 3 halves. Let's combine what we know how. I know how to deal with those fractions. 5 halves plus 3 halves is 8 halves. 8 halves is better known as 4. And let's see, I've got 10 plus 4 plus 3, that's 17. And so what I get is 21. Let's see what our units are. So ask yourself, can you figure out the units on this? It's right up here. Okay, this is kilometers per hour, and what we're finding is a distance. So what we're going to turn that into is kilometers. This train traveled 21 kilometers. And that truly is the value of this integral right here. Now, a lot of the time in this unit, when we've seen an integral, we immediately start finding antiderivatives using the fundamental theorem of calculus and proceeding that way. However, if you're asked for a Riemann approximation, which we weren't here, or if you can use areas of rudimentary shapes from geometry, then we're totally allowed to do that. So that's what we've done. 21 kilometers is our solution, and we're moving on. Here's an example of a very standard particle motion question. Why do we call it particle motion? Because if you think about it as a particle, the math is really, really easy to do. Something that has no width, think of it as like point motion. It's something that has no size. Now, it could be a football or a car or a person or a whale or a spaceship, or it could be really anything that's moving. And we need to know how to deal with those contexts. But for now, let's just start with a particle. Okay, in this one, we're told the velocity. We're told that it's in miles per hour. And this one is a more interesting velocity. I mentioned that in our first example that sometimes they're going to be more interesting than just linear, and this one is quadratic. And so we have a couple questions here. We need to talk about distance and displacement. So before we get into the nuts and bolts of it, let's talk about what those mean. Last time we discussed this was actually back in the vectors unit. So total distance would be something like this. If I walked 3 blocks east and I walked 4 blocks south, what is the total distance that I traveled? Well, I traveled 3, and then I traveled 4, and 3 plus 4 is 7, so that would be 7. But what's my displacement? Remember, displacement is your change in position. How much did your position change? And so that would be like if I measured from the starting point to the ending point. And so are we 7 units away from where we started? No, we're not at all. Remember the Pythagorean triples. This is a 3, 4, 5 right triangle. And so our change in position, we are only 5 units away. Now, this is a made-up example I just came up with because I wanted to illustrate for you, again, the difference between distance and displacement, because that's going to be important to understand what we're about to do with the calculus. Let me make up one more little example just to make sure this makes sense. Okay, so this example is going to have me in it. And so I get to test out my drawing skills here with my new little pad. And here's me. And imagine that I hop forward 3 times. 1, 2, 3. And then, just for fun, I hop backward 1 bounce. And so now this is the location where I'm at. And so we're going to try to answer 2 questions. What is the distance that I traveled? And what is the displacement that I have? So how far did I travel? I jumped 3 forward and I jumped 1 back. So I jumped 3 forward and 1 back. For displacement, I jumped 3 forward and 1 back. Notice the difference. Okay, I'm only 1, 2 units away from where I started. Here, I jumped 3 forward and 1 back. So this notation may not be really helpful, and I'm going to try to beef this up a little bit. What might be more useful is if we thought about it as the absolute value of those moves, because that negative saying I did move backward, but for distance, we're going to be taking the absolute value of that down for distance, and then for displacement, we're actually going to be taking what it is. It's backwards, so it's a minus. Or we could actually do 3 plus -1, okay? So, and I better write this in. So the distance was 4. Okay, so with that said, I'm going to clear this stuff off the screen. and let's get actually into this question. All right. What distance does the particle travel? What is the displacement? All right, in terms of calculus, which one do you think is easier? It's kind of hard to say, actually. One way that might make this a little bit easier to understand is if we could graph it. And here is my new little tool that I'm very, very happy to unveil. This is my TI Nspire emulator. Now, the reason I'm bringing this up, when you work on your assignment, I'd like you to use a calculator. And part of the reason for that, or a couple of reasons for that, is number one, we're going to run into some really weird functions that are difficult to integrate. And the second reason is when we're dealing with real world applications, it's often better to have a decimal as our answer so it actually makes sense to us. Okay, so I want to graph, and so I can't click here. Oh, I can. Cool. Learning the technology. Guess I can. So I can click there. If I want to graph, there's a couple ways to do it. We can go to the magic menu. That's obviously a wonderful thing. There's another way. You can hit Tab, and that'll bring this up right away. And so I'm going to graph this equation. Remember, your calculator is asking for x right here. It's not asking for t. And so we're going to type this in terms of x. So here I go. X squared minus 3x plus 2. And we'll see what this thing looks like. Cool. Okay. And as I look at this, one of the things that jumps out at me is that my window range goes from -10 to 10, but this question is very clear. It only asks about 0 to 4. And what about part B? Only asks about 4 seconds. So I want to change my window to make sure I'm looking at only the relevant domain of this question. And so we'll get rid of that. We'll turn that into 4. Or excuse me, I needed that to be 0. Okay, so delete that. I need a 0. I'm going to go up to 4 because that's as far as this question goes. And then I think maybe I'm a little bit zoomed out here as well. Maybe I'll try -2 and 5. And if that doesn't work, that's okay. I'll come back and change it. And yep, it looks like up here I've chopped off a little bit of the top of my graph. And so I want to come back and fix that. So menu, and we'll do the window zoom, window settings, and I'm going to change this. I don't know. I think 8 would probably be big enough. Okay, there we go. And so one thing that I want you to see right now is as we look at this graph, in comparison to what we talked about with going forward and going backward, right here, we're above the axis. Now, in terms of velocity, what do you think that means? If the velocity is above the x-axis, that means it's positive, so we're moving in the positive direction. That's like when I jumped 3 jumps forward. Right here for a little bit, it goes below the axis. That means it's going down, or it's going in the negative direction, and then it goes in the positive direction again. So what's easier to find? The displacement's going to be easier to find. The displacement is just a direct integral. In fact, let's write out what that would mean. So I need to switch to a pen real quick. That integral is just going to look like this. Integral of the velocity function with respect to time from 0 to 4. Okay, and then I want to show you how to do that in the Nspire. And remember, the reason that works, the reason this is not too hard, was the same reason my displacement example before worked. All we did is we took the 3 jumps forward and subtracted the jump back to get 2. Okay, and so we're just going to do that exact same thing here. Now everything good happens in the menu, recall. We're going to go down to Analyze Graph, and then we have an integral command. And over here on the left, we know that we're looking for an integral, so let's select the integral command. When we do that, it's going to ask for our bounds. This is one thing I really like about the Nspire is it uses common language. So we call these numbers bounds. They also call them bounds. That makes it really nice. So my lower bound, 0. I'm typing it in because that's what I wrote on my integral. And my upper bound, it's going to ask for it. How generous. They're going to ask for that as well. I'm going to type that in, and here we go. Okay, so it shaded it in. I also really like that because then it shows me, the calculator shows me what it thinks I meant. And I certainly did want it to shade all that. And boom, there you go, 5.33. It tells me, thank you very much. And so 5.33, that's displacement. What are the units? We started with miles per hour, and that means that these units are in miles. Awesome. Now we need to know the distance that we traveled. So is the distance going to be greater or less Remember in my little leapfrog example I did over here, I jumped 1, 2, 3 forward and then 1 back again. And so the total distance was 4, but the displacement was only 2 because I only moved a distance from start to finish. That distance was 2, but 1, 2, 3, 4 was the total distance traveled as compared to the displacement. So we have to account for the fact that on our graph, we have a little section here that's below the axis. And so I'm going to grab this, oops, remember click and hold, and then I'm going to just kind of drag that out of the way for now. We'll come back to that later. And so what I need to do is I need to incorporate that absolute value like we talked about before. And so as far as my integral goes, I'm going to have an integral of that first section that goes from 0 to, actually, I don't know where yet. So of the velocity, and then plus some other integral. And let's connect that back to the graph. So my first integral is going to be this section right here. My second integral is this section right here. And think about it. What would the value of this first one be? I don't know the number, but I know that it would be positive because it's above the axis. What about this one? We know that would be negative because it's below the axis. And so what I need to do over here when I'm writing this out, I need to put this second one in absolute value because it's negative and we're wanting the absolute value for the distance, for the total distance. So v dt, and again, I don't know my bounds yet. And then I'm going to look back at the graph again, and I've got this third region out here to the right. And so this I know is positive because it's shaded above the axis. And so my final integral is I'm going to go plus some integral, and I'm going to go up until 4 of the velocity. And that then will tell me my total distance traveled. So there's a little bit of pre-thinking involved in this. I mean, this is a little bit involved. In fact, we're not even done with our setup yet. We're not done with our bounds. So we need to go back and figure that out real quick. Okay, so what I need to know then is I need to know what is this value right here. And it'd be nice if I could hover like in Desmos and it would tell me. The TI Nspire is not that kind though. So what we're going to have to do is we're going to have to go into the menu and we're going to go down to Analyze Graph. And what is it that I want to know? Those are zeros. So I'd really like to know that 0. And I'm going to set my lower bound somewhere to the left of it. I'm just going to use the cursor. I'm not going to type it in because I'm clearly to the left of it right now. And I'm going to move to the right. And it says right down there at the bottom, looks like we have 1, 0. Okay, so that makes it kind of nice. I'm going to find the other 0 while I'm at it because there are 2 of them there. So Analyze Graph, 0. And I'm going to set my bounds right around it. So 1 and 2. And actually, that's kind of a relief because that's going to be really easy to type in then. So my first interval, I now know, goes from 0 to 1. My second interval goes from 1 to 2. And then my final interval goes from 2 to 4. And so that now tells me what is it that I need to type into the calculator to find these 3 values. We'll add those together, and then we will be done. Before we continue with this, I'd like you to make a prediction. Do you think that this value for the distance is going to be greater or less than displacement? There's one of these quantities that often, but not always, is greater than the other one. And I'd like you to make a prediction right now. Maybe in your notes, just circle or put a little asterisk next to the one that you think will be greater. And then at the end, after we know this value, then we'll go back and see if you were right or not and why or why not. Okay, so let's get to the calculations. I do want to make a note. We could absolutely do this by hand. I don't feel like it. And I want you to actually practice the calculator skills because we're already pretty good at dealing with stuff like this by hand. The IB test is timed, and so we want to be efficient, and so we need to make sure we have those calculator skills so when we need them, they'll serve us well. Okay, so let's get to integrating. So Analyze Graph, I'm going to need an integral, and I'm going to take that from, according to over here, from 0 to 1, 0, enter, 1, enter, and I get, oops, I need to grab that and get that out of there. Okay, 0.833. Now, before I stop this and go back and write all this down, I'm just going to leave them on here, and I'm going to find all 3 of these for the time being. So menu again, another integral. Okay, so Analyze Graph, integrate. This time we're going from 1 to 2. And it popped out a negative number. Not a surprise at all. Totally expected a negative number because it's below the axis. And one more. So this time, Analyze Graph, integral from 2 to 4. Okay, and so see how quick that is to get those values? That didn't take me hardly any time at all. Versus if I had to do all of it by hand, it's pretty tedious. This is a trick you can now use that you know it to speed up your assignments a little bit. Okay, especially now that you already have really good skills of integration. So I've got these three numbers. I'm going to go back and I'm going to scribe those down and we're going to add them together and see what we got. So it'll take me just a minute here. So please bear with me. 0.833. 0.833. And what was the next one? Was it negative 0.167? It was negative 0.167. I'm going to go plus 0.167. Why did I do that? Well, because it says absolute value right here. Okay, and so we intentionally made sure that all of our negative integrals were made positive. So we've got that right there. And then let's get the last one on there, and that would be 4.67. Okay, so plus 4.67. Wonderful. All we need to do now is add those together, and let's see what we got. 0.833 plus 0.167 plus 4.67. And what do I get? 5.67. 5.67 miles. So let's go back to your prediction. Did you predict that distance would be greater, or did you predict that displacement would be greater? Okay, in this case, it turns out that distance is greater. Now, the total distance isn't always greater, but it's never less. They could be equal. Like you could go 3 steps forward and then 2 steps forward. Okay, and then they'd be equal. 3 plus 2 is 5, 3 plus 2 is 5. But if you did 3 steps forward and 2 steps back, your total distance is 5. But your displacement is 3 minus 2, and that's 1. Okay, so displacement will never be greater. Distance will never be lesser. That's a quick check you can make on yourself. Maybe there's a way you can remember that, and that'll be helpful. Okay, one final example, we'll be done. Okay, this one is going to have particle motion with an initial condition. Hooray! Okay, Jenny's going to go for a 90-minute run. She's going to start at mile marker 134 on the road. That's the initial condition. She runs at 6 miles per hour for the first 60 minutes, and then her speed is modeled by a function, which is given there, some sort of exponential decay model. Okay, and that goes for the final 90 minutes. Wow, 90-minute run, what a good runner. Okay, so we have 2 prompts there. Number 1, write a piecewise function to describe this situation. What a great chance to review piecewise functions. So let's try to write that up. Okay, remembering what a piecewise function looks like. And we're going to write out her velocity. And so for those first 90 minutes, what is she doing? She's running at 6 miles per hour. So boom, 6, there's your y value. And she's doing that. Okay, we got to be a little careful of how we describe this. Okay, the units on that were miles per hour. And so they're telling us our distance unit is miles and our time unit is hours. So whatever I write here for my condition or for my domain, I need to write that out in terms of hours. And so if she did that for 60 minutes, that's 1 hour. So that's from 0 and t and up to 1 hour. Okay, that could be a little confusing because it says 60 minutes, but 60 minutes is 1 hour. Okay, so there it is. They gave us for the next section 6 multiplied by 0.9. Looks like Jenny maybe is starting to get a little bit fatigued. She's slowing down to the x minus 1, and she's going to do that from 1 up until 1.5 hours. Okay, and so there is just one little issue with what I've written in this piecewise function. So maybe you need to pause the video and see if you can find it, because I actually have made a mistake. See if you can see it. Okay, the issue is right here. I'm saying that t is equal to 1 right here, and t is equal to 1 right here. So if you plug in a 1, it is really unclear about where it should be plugged in. And so it doesn't necessarily say in this question which way it needs to be. However, it can't be like it is right now. So what I'm saying is it doesn't matter if I erase this one or that one. I'm going to erase this one because this is just where my pen happened to land. So that's what I'm going to erase. But that's part A. Okay, part A is done. Let's go to part B. We want to write and compute a set of integrals that finds Jenny's location at the end of her run. Awesome. Okay. And so if we're going to know where she is at the end of her run, and we mean milepost. So we started at mile marker 134. If we're going to know where she ends up, we need to know where she started. Okay. And so I'm going to write this as it's going to be her position. Redo. Everybody gets a redo, right? So redo her position and her mile marker. Much better. Her position is going to be where she started, so 134, plus however far she ran. I mean, think about it this way. Let's say she ran 6 miles. She started at 134, and then she would end up at 140. She ran 6 miles. I don't know how far she ran, but I do know how to figure it out with integrals. Okay, and she had 2 different things that happened in her run. First of all, she ran from 0 to 1. I'm just pulling that right off of here, by the way. And she ran at a speed of 6. And then, ooh, that's a plus sign. Plus. And then she started to slow down because, I mean, wouldn't you be tired after running for an hour? And so integral from 1 to 1.5 of, and then here we have that function. So 6 times 0.9 to the t minus 1. Okay, and it dawns on me that there should probably be a t. X is a pretty easy letter to fix to match that. Okay, so make that a t. T minus 1 dt. And so part of this is easy. Okay, so I can definitely take 134 and figure out what this next part of the integral is going to be. 0 to 1, or an hour at 6 miles per hour, is 6 hours. Okay, so that's pretty easy. If you want to go through the steps, go for it, but it's a little more intuitive than that. This next one, boy, oh boy, that doesn't look fun at all. So what can we do? Let's pull up the calculator. This is a really good example of why we need the calculator in our life. Okay, and so I'm going to come back to here. I'm going to clear this off. So menu, action, delete. And yep, I'm sure. I'm very sure. Okay, and let's graph it. Remember, the quick way to get that is to hit tab. Tab is going to bring this up, and so now we can type in our function. And so I get 6, and I'm going to just plug in this real quick. Okay, and there is our function. And we're going to integrate that. It says right here from 1 to 1.5. So let's integrate. Analyze. Oops, I hit the wrong button. Okay, redo. So menu, analyze, and integral from 1 to 1.5. And we get 2.92. Okay, so she did slow down a little bit. In a half hour, if she had not slowed down, it would have been 3 miles, but she did slow down a little bit, just as we expected. Okay, so 2.92. So thanks, calculator, by the way, because that was not going to be very fun at all. And so now we can figure out exactly where Jenny ended up. 134 plus 6, that's 140, and then we get 142.92. So she finished at mile marker 142.92. And then how did they ask that? Her location. So I'm going to put that as mile number 142.92, or 142.92 miles from the beginning of the road. Okay, but now we've answered that. So we needed that initial condition, or that boundary condition is what the math word for it is, in order to figure out. You have to know where you start in order to know where you ended up. Now that's different than the previous question. The previous question said, how far did you travel? The one we just did, it was, what is her displacement plus what was her starting point? So if you know where you start, you know how far you go, you can figure out where you end up. Hope you enjoyed this video. I hope it was legible, and I hope you could hear, because I'm testing out a lot of new things. And I hope you have a good time trying the calculator in class, and this was helpful to get that. And if not, talk to me, I'll help you out, okay? That's all for now. See you next time.